Hi, I'm Yaohua Wang. I will be presenting FIGARO. DRAM latency has long been a system bottleneck. Our goal is to reduce DRAM latency by DRAM caches. Existing DRAM caches augment DRAM with small but fast regions to serve as caches, but they have two issues. They use coarse-grained DRAM data relocation, and corresponding latency increases with the physical distance between slow and fast regions. To improve this, we propose FIGARO. The key idea is to use the existing shared global row buffer for data relocation, and this enables fine-grained DRAM data relocation at a distance-independent latency with low overhead. Based on FIGARO, we designed FIGCache. The key idea is to cache only small, frequently accessed DRAM row segments in DRAM cache. This helps to improve system performance by more than 16% and reduces energy consumption by almost 8%. We conclude that FIGARO enables efficient DRAM data relocation and helps FIGCache to outperform existing DRAM cache designs. Here is the outline. First, I will start by introducing some background on DRAM. DRAM is organized hierarchically. A rank is composed of multiple DRAM chips, and each DRAM chip has several banks. Each bank contains multiple subarrays and a global row buffer, and each subarray is composed of a two-dimensional array of DRAM cells. Now I will introduce existing DRAM cache designs. We identify two main inefficiencies on existing DRAM caches. First, they are coarse-grained, which hinders the potential of DRAM cache. And second, they add significant area overhead and complexity because they require many fast subarrays interleaved among normal ones. We find these two inefficiencies are caused by the data relocation substrate employed in existing DRAM cache designs. To solve these problems, we propose FIGARO. There are two key observations. First, all local row buffers in a bank are connected to a shared global row buffer. And second, the global row buffer is fine-grained compared with the local row buffer. The key idea is to use this global row buffer as a bridge to transport data among subarrays. Based on the above observations, we propose FIGARO, a fine-grained DRAM data relocation substrate that relocates data across subarrays at column granularity within a chip and cache block granularity within a rank. FIGARO has four key features. First, it is fine-grained, as it allows cache block level data relocation. Second, it is distance independent. Third, FIGARO has low overhead, about 0.3 DRAM chip area. And fourth, FIGARO has low latency and energy consumption. Based on FIGARO, we designed FIGCache. Key idea of FIGCache is to cache only small, frequently accessed portions of different DRAM rows into a DRAM cache. FIGCache uses FIGARO to relocate data into and out of the DRAM cache. This overcomes the inefficiencies of existing DRAM cache designs. FIGCache introduces a text store in the memory controller to store information about which row segments are currently cached. The DRAM cache part of FIGCache can be implemented with large flexibility. FIGCache has two main benefits. First, it has fine-grained caching granularity, and second, it has low area overhead and manufacturing complexity. Next, I will explain our experimental methodology. We use Simulator for performance evaluation and select 20 8-core workloads. At comparison points, we use conventional DDR4 as baseline, Lisa Vela as the state-of-the-art, and our FIGCache with slow and fast subarrays, and two ideal cases of FIGCache. Next is our evaluation results. Here are the performance results for our multi-core system configuration. The y-axis is the speed up, and the x-axis shows the workloads. Different bars represent different comparison points. The blue one is FIGCache slow, and the green one is FIGCache fast. The average performance gain of FIGCache is more than 16% across all workloads. We conclude that benefits of FIGCache increases as workload memory intensity increases, and both FIGCache slow and fast outperform the state-of-the-art Lisa Vela, and FIGCache fast approaches the idealized versions of the DRAM cache designs. And thank you very much. To learn more about FIGARO, please refer to our paper, and I would be happy to answer questions.
Thank you for the talk. There's one question about how much more area do you need to support a new relocation operation?
How much? You mean how much more subarrays, right? Or
metal resources, but that means transistor. So the original question says how much more metal do you need to support a new relocation? Interconnect. Okay. Interconnects. Okay.
Yes.
The question is about
thank
interconnects.
You very much for the question. Okay, thank you very much for the question. And for FIGARO, we use mostly the existing structures so that the overhead is very low. It's about 0.3% of the DRAM chip area. So additional overhead.
Right. Do you know whether that's mostly dominated by the interconnect, or are you calculating storage?
Yeah, they mostly dominated by some simple muxes to choose source and destination or column address within a DRAM chip. And yeah,
right.
we use the existing interconnect structures.
I see. So there's no change on the interconnect, but the changes are mostly due to the logic. Thank you very much.
Right.
The next question is, thank you. So the next question is, how is this concept different from row clone?
Oh, okay. The major difference between row clone and FIGARO is that row clone copies an entire DRAM row at a time, so that the granularity is an entire DRAM row, which is typically 2 kilobytes to 8 kilobytes. And for FIGARO, the granularity is a cache block, which is 64 bytes. So this is a major difference. And some small difference is that besides this major one, other ones are in FIGARO, we relocate data among different subarrays, while for row clone, they relocate data within a subarray.
That's great. Thank you. So the next question is from Jagadish Kotra. How do you manage the increased remapping information for relocated blocks with fine-grained caching? Do you keep this remapping information in DRAM? If so, it looks like your scheme requires more than one DRAM access for requests that miss in on-chip cache. Is that correct?
Okay, I see. We do not remap the address actually, because we use the fast subarrays as in DRAM cache, and we also employ text store in the memory controller so that you do not need to access DRAM twice to get the data, because you can know at the memory controller side whether the data is in the cache or in the normal subarrays, so that you can check first at the text store and then access the data in the right place.
I see. So if it misses in the on-chip cache, then the access is going to the original location, right?
Yeah.
Okay, thank you. Okay, the next question is from Hao Luan. Does FIGARO require to modify the circuitry of DRAM? If so, can you comment on the challenges to realize the concept?
I'm sorry, I can't get to modify which part.
The question is, right, the question is in the Q&A. The question is about, does FIGARO require to modify the circuitry of DRAM? If so, can you comment on the challenges to implement this modification?
Modification. You mean security or?
About the changes of the DRAM chip. Is it very challenging to change the DRAM inner circuit? And what would be the challenge to change the DRAM inner circuits?
Yeah, we just need to add a few muxes to choose between the source and destination column address, and also we need a register for source row address, and nothing else are necessary. So we don't think this would be of high complexity.
I see. Thank you.
Mm-hmm. Okay, thank you.
All right. Is there any other questions from the audience?
Hi, I suppose I can speak out my question.
Sure.
Mm-hmm.
Yeah, I'm thinking this in-DRAM cache is like the L1 L2 cache, but when we have the cache line is 64 bytes length, and it is already a better trade-off between the benefiting from the spatial locality and avoiding bringing useless data into the cache. But when we come into this in-DRAM cache, it suddenly become a 1K byte size. Can you explain why this can be a different trade-off between the cache size in the old L1 cache and this kind of DRAM cache?
Okay, you mean okay? The trade-off here is I think for the old L1 L2 cache, the cache block size is due to the DRAM IO interface, because it's 64 bits, right? And then, but for our in-DRAM cache, we do not have such limitation. We do not, I mean, we do not limit it by the chip IO, so that and also we have evaluated different DRAM segment size, and to show the sensitivity of such caching granularity.
Yeah, I see. Thank you.
Mm-hmm. Thank you.
Okay, there's one more question on the Q&A panel. How do you schedule the data relocation? It can not happen during regular access. Is that correct?
Yeah, it cannot happen during regular access to the either the source subarray or the destination subarray, but we will not affect the access to other subarrays or other banks.
Thanks.
Mm-hmm.
I have a last question. Sorry. If
Go
it is
ahead.
already, so how do you handle writes if the data is already cached in a different location? So do you write it to the original DRAM row or to the cached DRAM row?
I'm sorry. Can you repeat the question? Or
The question is about how do you write to the cached block? Do you write it to
DRAM
the
cache?
in-DRAM cache? So if a block is in the in-DRAM cache, when there's a write, do you write to the in-DRAM cache location or the original location?
Oh, okay. I got it. Yeah, the write will be directly going to the in-DRAM cache if there is a hit, and then the dirty data will be right back into their original place when eviction happened.
Okay.
Mm-hmm.
Thank you.
Okay, thank you.
All right, so there's another follow-up question from Pocket Jen. Do you interrupt the scheduling of data relocation if there is a priority request to that page? This is
No,
again about scheduling.
for our current design, the relocation process cannot be interrupted.
Mm-hmm. Okay, Thank you.
but yeah, this can be modified. Yeah. Thank you.
All right. Thank you again for the speaker. Let's move on to the next speaker.
Thank you.